Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, well, let's get started here. I'm very happy to introduce Karu from, I hope I'm pronouncing that right.
Yep.
That's even his nickname. I won't even attempt to pronounce his real name. Karu from UT Austin, where he's been working in the CHIPS project with Doug Berger and Steve Keckler. And let's see, without further ado, I'll let Karu tell us about his work.
Cool. Good morning. Thank you all for being here. So I'm going to talk to you a little bit about my dissertation research, which has been in the context of the CHIPS project. So it's a relatively big project, and towards the end of the talk, I have a formal acknowledgement slide talking about contributions from the other folks. What I really want to do in this talk is give you a feel for the main design principles involved in this research, and kind of have you understand some of the intuition behind some of the design decisions we made, and some of the concepts behind this architecture. So let me start off by looking at some motivation and try to really understand where processor performance is coming from, which I just heard that you guys don't hate introduction slides like this, which are very high level. So I'll try to get through this very fast. So on the x-axis we have time, and here I am plotting processor performance. This is for the Intel x86 line of process. The brown curve shows performance. The first thing to note here, of course, is it's a logarithmic curve, effectively been doubling performance every 2 years. And now you look at the green curve, that is plotting processor frequency, and the immediate thing you notice is frequency has been doubling every 2 years as well. The obvious conclusion is primarily processor performance has come about because of frequency growth. As of 2003-2004, we ended up at a point where we ran out of techniques to increase processor frequency, both almost from the device side and from the microarchitecture side. So going forward, Right. So this is uniprocessor performance. So hyperthreading wouldn't exactly fall under uniprocessor performance. The other thing, you're absolutely right. Microarchitecture changed a lot. So 1990 is Pentium. Oh yeah, absolutely right. You're absolutely right. So 1990 was Pentium, at which point we had many of those techniques. So you had a level 1 cache, you had level 2 cache almost. You had an FPU, you had all kinds of integer units right there. And if you measured IPC there, it was a little less than 1. Instructions retired per cycle by the processor, and you measure IPC at 2003, it is actually worse. At this 20-stage pipeline, your branch misprediction latency is so bad that if you try to run these backend programs or something like Office, you're actually retiring fewer instructions every cycle. The only reason your program is running faster, or the biggest reason, is you're running at 3.8 gigahertz. That's why bottom line wall clock time is faster. Yeah, so yeah. Yeah, so I think so the point really is, so frequency here does not refer to just device speed. This has two components to it. One is the device speed, which grows linearly with the transistor size, and about 40% every year. Okay, every 2 years actually. But however, we've been able to double frequency. The remaining component is the microarchitectural innovation. So the Pentium there was a 5-stage pipeline, and in 2003 you had 21 stages. So there's been a lot of microarchitectural innovation that has gone into helping us build these deep pipelines. So we've been able to pipeline the L1 caches, there's the trace cache, we've been able to pipeline even functional units. So the 64-bit data path is actually pipelined in 2 stages. So, oh yeah. It is frequency. These have contributed to increasing frequency, not concurrency. So let me go ahead a couple of more minutes and then come back to the discussion. So going forward, if you yeah, let's spend 30 minutes on this and then I'll jump to conclusions. Okay, all right. So anyway, so going forward, because we ran out of these techniques, what is going to happen is we'll not be able to use these microarchitectural techniques to improve frequency. The best frequency growth is going to come primarily from device speed, which is projected to be 15% every year or 40% every 2 years. So that's shown by the dotted line. And if you were lucky enough to do all kinds of funny stuff with the programs and you manage to track frequency, at best performance growth is going to follow that dotted line. Okay, it's a significant shift from what we used to before. And there are people in the devices camp who believe device speed will completely stop as well. Essentially because now your channel has become so short and process variation is a big deal and leakage current and all these things, your frequency growth may completely come to a stop. As a result, Moore's law will simply mean device integration, more devices on chip but not running any faster. If you do that, then processor performance is going to completely stop for uniprocessors. So the main point of course of all this is, so far we've been getting performance primarily through frequency. Going forward, we need to get performance growth through something else. And that something else is what I label concurrency. You need to start doing more parallel things on chip instead of just trying to do a small number of things really fast. So that's the main point of this slide. So are there any more questions on that? We can have more discussion on that before we proceed. Alright, so let's look at yet another high level slide. So here I've shown the system stack all the way from the algorithm down to the hardware. There are a couple of points here. First is, if you look at the ISA, it has been fundamentally sequential for the past 25 years or more. It hasn't changed that much. Yeah, we've added MMX extensions, SSE 1, 2, 3, 4X, but those have been primarily for a very targeted set of applications. The other thing is, the job of mining concurrency or finding out parallel instructions is primarily being on the hardware. We think about programs sequentially, languages are sequential, compiler also reasons primarily in that domain. The hardware mines concurrency. And at this point, we've been able to get very moderate amounts, in fact demonstrated by these 4 ALUs here, which stands for more than just the ALUs. This goes back to the point you were raising. It stands for concurrency in the memory system. We've added wider register file, we've added wider fetch units and all that. So this represents all of that, but it's very moderate. In fact, the widest superscalar processor is 4 issue, and that's right there. Going forward, if we need to get more concurrency, the hardware is going to look like this. There is going to be much more concurrency fundamentally in the hardware. The question really is what the rest of the stack looks like. It's more than just architecture. It's a system level question. How do we find this concurrency? How do we express it through these different layers in the stack? Finally, who finds the concurrency? Which layer of this is kind of primary job is to find the concurrency. So if you look at what industry wants to do, the basic approach is let's create multi-core chips where each processing unit is actually relatively simple. The amount of concurrency exploited by that is relatively small. The primary job of finding the concurrency is now pushed to a magic parallelizing programmer, whose job is to basically look at the source code, you look at your algorithm, do all kinds of trace analysis and find your concurrency. And you express it to the hardware using this really low level primitive called threads. It can be very hard. If you're a really good multi-thread programmer, maybe you'll say it's not hard, but for most people it's quite hard. So that's the basic approach. Undoubtedly this can work very well for some programs. So databases, web servers, in fact it's already working great, work very well. But for general purpose programs like Office or gzip, LaTeX or anything that I write, maybe you all don't write programs like this, but the bottom line is it's very hard because there are not very sophisticated software tools and debugging tools to write these programs. The other perhaps even bigger challenge is a vast existing software code base which perhaps needs to be significantly redesigned and rewritten to benefit from this approach. There's no way you can just take these programs and run it on a multi-core chip. It's not going to be any faster. It'll run at exactly the same speed 2 years from now, 4 years from now, 6 years from now. Just because you put more cores on it, nothing's going to change. So what we are proposing is a technique to continue this performance growth for uniprocessors. So the basic approach here is the following. We keep maintain conventional software design methodology, so you don't need to write using threads or go to this very different programming model. Instead, we renegotiate the compiler hardware interface by proposing a new class of ISAs called Edge. So Edge stands for explicit data graph execution. The 2 main points here are, instead of expressing programs as sequence of instructions, we now represent them as sequences of blocks. And each block is essentially a data flow graph. By doing that, you made the dependencies and the concurrency explicit in the block. So it's much simpler for the hardware to mine that concurrency. And secondly, we built a scalable microarchitecture that implements the ISA. The main point of the microarchitecture is essentially distributed, so it's in scale with technology. You can grow this to be bigger and bigger to exploit large levels of concurrency. So this is a very high level summary of our approach to extract more concurrency for uniprocessors.. processors. So here's the outline of the rest of my talk. I'll spend a little bit of time talking about conventional microarchitectures and why is it that we just can't build a 16-issue Pentium 4 or a 16-issue AMD. What is the fundamental scaling problems for conventional microarchitectures? And then I'll spend a little bit of time talking about the ISA, the actual microarchitecture that implements the ISA, and some performance results. I'll talk a little bit about future work and conclude my talk. So here is a high-level pipeline diagram that represents what most of today's conventional superscale processors look like. So I'm going to walk through this multiply instructions through the pipeline to demonstrate what are the scaling problems, why is it that we need to go to a whole new ISA and a whole new microarchitecture. So the multiply reads 2 source registers and writes it to R4. So let's walk through what are the operations that need to be done. So first you fetch it from an instruction cache, then you go and do a decode or a rename and a rename. The main job and main thing you need to do during rename is essentially make sure that you have resources in the remainder of the pipeline to carry these instructions through. At that next, the instruction goes and sits in an instruction window. Here what essentially happens is you want to make sure that the source registers for this instruction have been produced. So here R1 and R0 need to be ready. This operation essentially boils down to reconstructing the data flow graph of all your live instructions in hardware. And this is a very expensive process, and the growth of the structure grows quadratically with the number of instructions you're trying to simultaneously analyze. So in this picture I'm showing what would be a one issue processor where you're always trying to find one instruction to execute. If you did much more, it would grow quadratically. So at some point the source operands are ready, then you go read the value from a register file, and then you go execute it on the functional units, and finally you go wait in a reorder buffer. So you need to wait in this reorder buffer because you may have executed these instructions out of order, and for speculation reasons and exceptions and all that, you need to retire these instructions only in the order specified by the programmer. So you wait here until this becomes the earliest instruction in the program, and then you can write the result into the register file. So these are all the operations that need to be performed for each and every instruction in your program as it goes through the pipeline. The main point here is there's a lot of bookkeeping logic for each and every instruction. You need to walk through all of this. Second, this is just a single issue architecture or something that executes one instruction every cycle. To get more concurrency, you need to grow all of these structures. First of all, you need more functional units. Let's see what that implies. It means you need a lot more area because you put more functional units there, plus additional area of cost created by these bypass paths. So a bypass path is essentially this wire that connects different stages in your pipeline so that dependent instructions can execute as early as possible. And this again grows quadratically with the number of instructions you want to issue every cycle. So this structure would actually be 16 times bigger than what you just saw before, which was a single issue architecture. This is just the functional units. All the structures need to go if you want to grow, if you want to mine more concurrency from the architecture. So instruction window needs to grow deeper because you need to look at more instruction to extract concurrency, plus because you're adding more ports to it, that structure grows quadratically as well. The register file also grows quadratically because the growth of the structure is a square of the number of ports that go into it. I just talked about the functional units. The reorder buffer is similar to the register file. It's a register array, so it grows quadratically with the number of ports. So bottom line of all this is, if you want to mine more concurrency using a conventional pipeline, you need to build lots of large structures. They all grow quadratically and they consume a lot of power, which is a big constraint. That really is the question we're addressing here. What is required to design a concurrent architecture for sequential programming? So in this talk, I'm going to focus on 3 of the main principles involved and not get into all of the engineering details that come about as a result of building such a chip. So the 3 principles are, first, you want to rebalance the compiler and hardware effort. Instead of spending so much time in the hardware reconstructing this data flow graph, which the compiler just did before it did code generation, you want to instead be able to express the data flow graph directly to the hardware. That's why you want to change the ISA. Second, you want to amortize these instruction level overhead. Instead of walking each and every instruction through the pipeline and spending so much bookkeeping logic, you want to do that at a block granularity. Let's try and take groups of instructions through the pipeline, thereby cutting down the overhead. And finally, because these centralized resources grow quadratically and very hard to build, you want to try and eliminate them, somehow build a distributed microarchitecture. So those are the 3 main principles, and I'll keep coming back to this through the rest of my talk. So a summary of this approach, basically, as I said, programs are encoded as blocks instead of sequences of instructions, and the data flow graph is explicitly represented in these blocks. And the microarchitecture is essentially a distributed one with mesh networks, thereby communication is always local. You don't have these complex bypass paths that are going from one function unit to every other function unit on chip. In terms of results, we've been able to demonstrate 5 times better performance and the best superscalar processor. In a little bit I'll define what exactly I mean by best, and actually building the full hardware and software prototype systems, and we're expecting full chips back sometime in the middle or late part of summer. We already have a working compiler that's providing code for in this ISA, using that for simulation results. That's what I'll be talking about today. All right, so let me now talk about the ISA and a little bit about the microarchitecture itself. So again, the 2 main principles in the ISA really are to be able to balance the effort between the compiler and hardware, and to try and amortize these instruction level overrides. So what we've done here is we've introduced a new class of ISAs called Edge. Edge stands for explicit data graph execution, and there are 2 main features of this ISA. First, it supports block atomic execution. Either you break a program into a sequence of blocks. These could be basic blocks, hyper blocks, or some other definition of blocks where essentially you grouped instructions together. The second main feature of the ISA is that it has direct instruction to instruction communication within the block. Thereby, if you have 2 instructions that are dependent on each other, you can exploit that dependence locality, which a superscalar processor cannot, because just walking these processes through the pipeline has these full bypass units to which you kind of just dynamically schedule the instructions without trying to understand that these 2 are really only these 2 are communicating. I want to put them close together. By making these dependencies explicit, you can actually give that information to the microarchitecture and exploit that. Across blocks, you still communicate through a shared name registers. So the logically centralized register file to which every block writes block output, and memory again is a single logical shared names. So those are the 2 main features of these class of ISAs. And let me now walk through an example to see what exactly this means and what it boils down. So here's some C code, and I'll show you what this would boil down to. Excuse me, in a RISC ISA. Excuse me, and what this boils down to in an Edge ISA. So first we need to look at the data flow graph to understand what's going on here. So here I've highlighted this for loop, and let's walk through what exactly the data flow graph for this and use that to understand what the ISA looks like. So the data flow graph is pretty straightforward. You want to take Z, add I to it, write it back to Z, increment I, and write it back to I. So if you're a data flow purist, you want to actually have this notion of control flow embedded in the data flow graph itself. So when you have the full data flow graph of the program, that thing will disappear. But since you're looking just at a section, it's just there for illustration purposes. So what would this look like in a RISC ISA? This is like x86 or Alpha or PowerPC or Spark. Here's a sequence of instructions. I don't actually want you to read all of these instructions. The main point here is the program has this sequence. Second, each and every instruction reads from a centralized register file. It is denoted by G1, G2, and so on over here. Second, the result of these instructions again goes back to the centralized register file. There is no notion of locality or trying to detect which are temporaries, which don't really need to go to a centralized register. In an Edge ISA, how this program would be represented is a sequence of blocks. Instead of having a sequence of instructions, we have these blocks. We have a control flow between blocks. Let's look at what the instructions of a block actually look like. Again, I actually don't want you to read all these instructions. Let me quickly walk you through some of the components of this ISA. First, every instruction has a label in front of it, denoted by the N0 through N8 over here. These labels are what we use to actually communicate the dependencies. So for example, if you look at the increment instruction, the N2 increment, it says the result of the increment needs to be sent to exactly N7 and N4. Again, this is not any kind of centralized result. It's telling explicitly these are the only 2 instructions that need the result of this increment. Instead of encoding sources, we now encoded targets in this ISA. As a result, the data flow graph is now explicit. In fact, if you walk through these dependence edges, the read instruction is reading from the centralized register file, sending its result to exactly one instruction. this is being communicated to another instruction, writes back to the register. So these dependence arcs encode the highlighted green portion of the data flow graph. In fact, if you looked at all of the instructions, you'd see that this makes the data flow graph explicit in the ISA itself. As a result, you know exactly what the independent instructions in the program are, thereby you can execute them in data flow order. That's our technique for mining concurrency. So I've talked about kind of the principles behind the ISA and an actual example. Let me very quickly walk through the role of the compiler and talk about how we actually build these binaries and build these blocks. So again, the compiler starts with the C code. The first thing it does is it creates a control flow graph of the program, at which point you essentially have basic blocks, which are relatively small. They have only 5 to 6 instructions in them. So we apply a set of control flow heuristics to grow these basic blocks into large blocks. So we call them hyperblocks, and the main techniques are function inlining, loop unrolling, and several other transformations that help us build large hyperblocks. The next step is what we refer to as some kind of intermediate code generation, at which point what the compiler basically does is looks at the instructions in this hyperblock and has a data flow graph representation. So this is still an intermediate representation where each node here represents an instruction within one of these blocks, and you built this data flow graph representation. Yep. Exactly. Yes. So in fact, let me, if you take this example right here, I have this S7 that is writing to actual centralized register file, right? So this is what I would call a leaf node. Instead, if I had another node here which was not writing to any place, right? So that you don't need to do anything there. So that instruction would never fire and would not in any way affect the architecture or affect when the block actually finishes executing. So you can do that. But the main technique for actually getting performance here is to speculate across blocks. So you map one block and then make a prediction on what the next block is going to be, and map both of these simultaneously on the hardware and execute them at the same time. So when I talk about the actual execution model, somewhat it becomes clear. You can ask the question again. Okay, so we have this data flow graph representation of the block, and the next step is a relatively important step. Here, what the scheduler, which is part of the compiler, does is takes this data flow graph, takes a representation of the processor topology. So in this implementation, we have a 4x4 array with a mesh network, and schedules the data flow graph to nodes in the processor. In fact, those labels you saw a little while ago in front of each instruction are basically slots in the processor. These are these N0 through N15. And the job of the scheduler is essentially to do this assignment. Which nodes need to be assigned to which labels? And the main heuristic it's using here is to take dependence paths on the data flow graph and map them to physical paths on the hardware. So this straight line chain S through S7 essentially gets mapped on straight line chain on the hardware itself. The main insight here is you want to reduce communication distances as much as possible and exploit the locality. Instead of having to broadcast stuff all over the place and spend a lot of time and area doing that broadcast. So that's the main intuition over here. The second point here, of course, is this is more of a microarchitectural optimization. These slots, they're just process slots. So as long as you have a processor that has 128 slots, you'll still be able to execute a binary that's been built for a different topology. It would just not perform so well because it has been optimized for a different communication pattern, whereas in a different architecture, you have a different network, so the physical dependence edges are different from what you compiled for. But in terms of correctness, you still don't have any issue about how to execute this program. Alright, so that's the job of the compiler, to take C code and eventually create binaries in ISA. So let me now talk about the microarchitecture implementation and how we actually execute this binary on the microarchitecture. Again, the main principle in the microarchitecture is to eliminate the centralized resources so that you can actually build something that's scalable. So here's a very high level diagram of what the microarchitecture looks like. In a little while I will walk through each of these tiles and actually demonstrate what is inside each of them. The two main concepts here are, you want to limit wire lengths as much as possible because it's very hard to communicate, it takes a lot of time to communicate across chip. You want to build these tiles and reduce the communication between these tiles to only short wires. In fact, all of the communication between these tiles happens always through these short wires, which are part of a three communication networks that we built inside the processor. The second, because we have followed a very tiled architecture, it has an inherent notion of scalability. You just need to design, in this case, just 5 tiles. You can replicate them multiple times to build a big processor. The second, because these tiles communicate through a very well-defined network and not through ad hoc bypass paths or ad hoc stall signals, there's an inherent scalability there. Already exactly said what is the communication possible, so you can just stamp out multiple of these and things would still work. Do you have a question? Exactly, yes. Yep. And that again goes back to the scheduler. It's the job of the scheduler to optimize those dependence paths and put them as close to the register file and the memory system. And in fact, it raises the question with register allocation and scheduling. So now we have a phase ordering problem, because if you've done your register allocation, you want to put dependent instruction close to those registers. And we are looking forward to technique where you can do both of them in one single phase, so that communication is reduced. Alright, so that's a high level principles involved in the microarchitecture. Let's now walk through each one of those tiles and see what is inside them and how that allows you to execute these blocks. So first are the execution tiles. So these actually have the main function units in the processor. The 3 other components in them are, we have some instruction storage space demonstrated by those buffers over there, and also storage space for operands. So this is where results of an instruction come and fall before they actually get executed. You can think of this as being similar to reservation stations in a conventional processor. The third component here is what is labeled as a router there. So the router's job is to allow you to communicate through this communication network that allows you to kind of design with scalability in mind. So those are the 3 main components in the execution tile. Next, yes.
This diagram looks very, very similar to Reservation.
Yes.
Previous slides back.
Mm-hmm. Right. Mm-hmm.
I wanted to ask again.
Okay.
Maybe for particular differences.
Sure. So the main differences between this and WaveScaler are that WaveScaler does not, this goes back to the speculation question from before, does not have the notion of control flow. So as a result, you would have to essentially execute each and every block that you statically built as part of your compiler, and not skip blocks that you know are not going to execute. That's an important distinction for irregular programs like SpecInt or even many desktop applications, because it's very hard to predict what the control flow is going to be statically. It changes a lot with the data that you have. So here what we can do is you map a block and you actually speculate what the next block is going to be and map it again out to the same hardware. So you can have those two executing at the same time. In WaveScaler, their notion of waves is just like basically what we have as blocks. You would have to essentially statically map all the blocks that the compiler created before you can go to the useful block. So the drawback, of course, is you're just doing a lot of useless work which you're going to throw away anyway. You need to maintain much more state in that approach. The second difference is, can have bigger performance impact, is speculation in the memory system. Again, because there is no notion of speculation there, the compiler needs to say exactly what the ordering of all the memory instructions is, which is again very hard if you're like traversing a linked list or some kind of recursive data structure. As a result, the performance can be very limited again for the SpecInt like program. Here what we do instead is memory requests come and fall into these data tiles, and they can just go into the memory system in whichever order they arrive. If you detect a dependence violation because a load arrived ahead of a store and the compiler actually said they should execute in a different order, you treat it just like control speculation. You flush this block and re-execute it one more time, and you have and you can kind of disable what we have as a dependence predictor to make sure that the second time you execute it, you don't have this violation. That's again a big win for trying to exploit memory parallelism, because it's very hard for the compiler to do all that reasoning. Yep. The cost of that is mainly, at this point, we have this global tile which is a centralized unit, and that is taking care of managing all of these bookkeeping logic and all of that. So why I call that as a cost is because the rest of this is kind of directly scalable, right? You can just keep planting more tiles, but that's a single point of communication where everybody needs to go. So that's where some of the drawbacks would come in. Alright, so that's the execution tile. Next are the register tiles, and these implement the architectural register storage. The main thing to note here again is they are very well partitioned and they are aligned on top of the grid. The other thing is, by having this approach of having them communicate to a very well defined array, we are able to build a register file of much bigger bandwidth and much more storage than a centralized register file that you need to build in a conventional processor. And again, these communicate through this same well defined communication network through the rest of the array. The next are the data tiles, which I mentioned just a little while ago. These implement basically your first level of cache. They are again very nicely partitioned and communicate with the processor using the same communication network. Next are the instruction caches. These are the first level of instruction caches. They again have the storage for the instructions and are very nicely aligned with the rest of the processor. So blocks can essentially be mapped across these tiles of unit and be streamed across the processor. They get very nicely lined up. And finally is the global tile that I mentioned a little while ago. The main responsibilities of the global tile are to sequence these blocks, and also has a block predictor which is somewhat similar to a branch predictor. Every few cycles it's making a prediction on what the next block is to be mapped on the processor. Alright, so that is
The processors have
explicit control over the cache. No. So we have somewhat of a notion of prefetch, but there is no explicit. You cannot explicitly manage this level of the cache. There is a second level cache which can essentially be configured like a scratchpad. So I can have a program that says, here is this big block of memory, fetch it to the cache before you start executing on it. So let me talk about how you would actually take these blocks of instructions, map it to the processor, and how exactly things execute here. So I'm going to explain this in terms of three operations: fetching a block, executing a block, and then committing all of the architectural storage of the block to architectural change of the block to the architectural storage. So block fetch is very straightforward. The global tile decides what the block to fetch is, it knows the address, and sends that command through one of these networks to the instruction tiles. These are, again, there is no broadcast here. They again go in a very well defined fashion, one hop at a time, and each and one of these instruction tiles gets this fetch command. It reads the value from its SRAM and streams it across the processor, shown by the horizontal arrow over there. As a result of this operation, it takes actually varying number of cycles for instructions to be mapped on different tiles of the processor. So fetch is not a single cycle operation, it's not a fixed cycle operation. So at this point, instructions are being mapped to resources inside the processor. Now block execution can actually begin. So execution has three main components to it. First, the read instruction of a block, read from the register file and send the results into the data flow graph. That essentially triggers data flow execution of the instructions in the block, and when all of the instructions in a block are done, essentially the leaf nodes in the data flow graph, or the last set of nodes, write back to the register file, or there's one instruction in the data flow graph that tells you what the next block to execute is. In this example, it's this final add instruction and this branch instruction. Let's tell you what the next block to actually go fetch is. Let's very quickly look at how that execution happens. So read instructions execute, send the results into the grid, and that triggers the data flow execution. Finally, the leaf nodes can execute. Their result goes back to the register file, and the branch result goes back to the global tile, so the global tile knows what the next block to fetch is. So bottom line of all this, block execution is a result of block execution. All register values have gone to the register tile, the branch result has gone to the data tile, the store values would have gone to the data tile. In this example, I have not actually talked about the memory system, but you can come to that at the end of the talk. So the final step of all this is to actually commit all of the results to architectural storage. So that, because we have the distributed model, you kind of need to detect completion and then start the transfer of these values for block commit. So when the register tiles in a block receive all of the writes for that block, they know that that portion of the block has actually finished completion. So that again, and the data tiles detect when all of the stores in a block have actually been received. So they use again one of these networks to communicate that information to the global tile. When the global tile knows that all of the writes have been received and all of the stores have been received for a block, they know that this block can be committed. They send a command to these tiles saying, you can now commit this block, at which point the register tiles transfer values from the temporary buffers to the actual architectural storage, and the data tiles transfer values from temporary storage actually to the level 1 cache system. That's when things actually get written to memory. Again, this can take varying number of cycles because you can have different number of writes and different number of stores in a block. So they wait until all of these results have been transferred and send a command to the global thread saying, I can actually acknowledge the commit, all the transfers have been done. So that's the final commit acknowledge phase. At this point, all your resources in the processor can actually be deallocated and you can start mapping the next block to these resources. Alright, so until this point I've kind of given you a logical explanation of how blocks actually execute. So we have a fetch followed by an execute, it's very serialized. However, as you may recall, I have these reservation stations in each and one of these tiles that let you map multiple blocks to the processor simultaneously. So what we actually implement is the following. Use these reservation stations to create a very deep instruction window, use control speculation to fill these instructions in the window. So as soon as you're done fetching one block, you make the next prediction and start fetch while that previous block is actually still being executed. So the main point here is you get this very highly overlapped execution of multiple blocks alive at this on the execution array simultaneously, and that's how we actually mine a lot of instruction level parallelism. Alright, so far I've talked about the ISA and the microarchitecture itself. Yes. You definitely get contention in the network but you don't get contention. Yeah, you don't get contention inside the execution tiles because of the following reason. Alright, so we have the storage, right? So what really happens is we break this up into chunks. So we have, actually I'm showing 128 here. You can think of 8 of these slots and allocate that and call that as a frame, right? Now you think of these 8 slots spread across the 16 tiles and that gives you 128 slots. Okay? Right, exactly. Yep, exactly. How do you handle what? More instructions than you. So actually, so the point is this. In this architecture, we support only fixed size blocks, and all blocks have to be 128 instructions. Okay. So if the compiler will never generate blocks that are larger than 128, and you have blocks that are smaller than 128, you fill the empty slots with no ops. But in a different implementation, you can think of other dynamic translation mechanisms that somehow manage the resources and make sure that you always have resources before you map them. Yes. Yeah. Right. Right. Yep. Yeah. Mm-hmm. No. So there is, so the firing of each instruction is completely independent of what else is happening in the block. Okay, so if you think of an add instruction that has 2 operands, so at some point the add will actually be fetched and its value will come and fall into the instruction buffer. Okay, and whoever the producer instructions for those add are, they may get mapped somewhere. At some point they'll execute and the results will come and fall in these buffers. Okay, right. Yes. And in fact, because of the way we have a protocol, sometimes the operands can arrive before the instruction arrives. So that doesn't really make a difference. Yes. So the dependencies are being expressed in the hardware. The issue is the issuing of the instructions is detected dynamically by the hardware. Okay, so I was here. Okay, so let me talk now a little bit about performance results and compare this against other existing design. So before doing that, the question really comes up, what is a meaning processor to compare against the TRIPS processor? So we looked at the Alpha 21264 and that's a balanced 4-byte machine. And really one goal of TRIPS is to understand what is required to build a balanced 4-byte machine. So that's the baseline I'm going to be comparing against for the remainder of a few slides. So main point here is we're getting performance by building a very deep instruction window and trying to get multiple instructions executing simultaneously. Yes. So balance so going back to the pipeline diagram from before, there are several components that make up a processor. So when you say balanced design, what you mean is none of these components has been over designed, and it's not like for most of your programs one single thing is the bottleneck. For different programs, different things are the bottleneck, and they have many times get averaged out. 4-byte basically means in that pipeline I was executing one instruction every cycle. So in a 4-byte machine you would be able to take 4 instructions through the pipeline at all points. As a result, at best case, if your program allowed it, you would be retiring 4 instructions each and every cycle. Okay, so the goal of the TRIPS is to be 16-byte, and we are really trying to understand what the implication of these decisions and all that. So yeah, so that's a good question. So we have not yet done a detailed analysis of all of the scalability issues. So we are actually attempting that as part of this work, and we did a little bit of that before going forward with 4x4. So my personal belief is that decision is kind of a function of what your application is and what your primary domain of interest is. And in this architecture, in this microarchitecture, there is a weakness that if you build an 8x8, your scheduler is not very intelligent, you're just wasting resources because you're not doing anything with them. So we're looking at another implementation where you move the register tiles and the data tiles inside one single tile, so you can use the different tiles to execute different threads or different programs if the ILP is limited, so you don't want to build a wide issue. So there are 3 main components to kind of experimental evaluation. I'm not going to talk about all of this in detail because it will take a lot of time. I'll just give you a flavor for the studies that we did. I can talk about the details during the one-on-one. So some of the things we did to see how sensitive is the processor to the ALU to ALU delay. Suppose we had 4 cycles between every dependent instruction, how much performance would we lose? We investigated things like the routing algorithm. Instead of always routing along X and then Y, what would happen if we routed along Y and then X? What if we did adaptive routing? Things like that. The second component is to kind of understand what are the complexity implications or decisions we made. So we've implemented the hardware, and we already know that because we had to build this routed microarchitecture, the OPN, which stands for the communication network, takes up significant area. In fact, in this design, it takes up almost 12% of the processor area. So we've already understood some of the lessons. Once we get the hardware back and run full programs, we'll know more of those. And really, finally, we want to understand kind of the breakdowns of all of the overheads. Because we have the distributed protocol, we lose so much. Because we have the scheduler that's trying to get the locality, we're able to gain so much. That's really what we eventually want to do, to understand where is it we're getting the performance from. And finally, all of this is also predicated on having high quality code, and right now we're still tuning the compiler, so going forward some of this will change. Yes? Yes, I am sorry about the acronym. So, no, that's fine. So OPN stands for operand network, so that was this router that I showed in the execution tile that is sending values from one functional unit to another functional unit. And LSQ stands for load store queue. So load store queue is the structure that does hardware memory disambiguation essentially. Alright, so let me very quickly talk about some performance numbers. So here again I'm comparing to the best superscalar processor, and that is the Alpha 2164 for our purposes. So the blue bar shows the performance in terms of instructions per cycle. So this is the number of instructions that as you execute the program you're able to retire each and every cycle. It's broken in terms of integer and floating point programs. So this is from the Spec 2000 suite. The blue, you can see that on average you get an IPC of 1 across all of these programs with the 2164. So on the TRIPS processor, on average you can get 2 times better on the spec-in programs, about 6 times better on the on the floating point programs because they have much more concurrency. So let me now give you an intuition of why we are able to obtain these performance. In programs like MCF, what essentially happens is you have a lot of level 1 cache misses. So in a processor like the 21264, that ends up creating a lot of memory latency. Here, because we built a very deep instruction window, you can send a lot of requests to the level 2 system, and as and when they come back, you can execute more and more instructions. thereby hiding the memory latency. In programs like parser, on the other hand, you're kind of mostly walking through this linked list. So fundamentally the amount of concurrency in the program is limited. So even though you provided such a wide issue architecture, not able to run any faster than 21264 itself. And other programs like twolf, dzip and so on, essentially because we built a much deeper instruction window, you can mine much more concurrency. You're all the time looking at more instructions, so you're able to basically find more parallel instructions. So those are kind of a feel for where exactly the performance improvements come from. And let me very briefly talk about equec because it's interesting compared to the rest of the floating point program. It has a very high level to cache miss rate. As a result, you're able to hide this memory latency only to some extent, beyond which all the time you're going to memory and just takes 130, 140 cycles for request to come back, and even though you've provided such a deep instruction window, it's not deep enough to hide that much of latency. So techniques like building a prefetcher or a correlating prefetcher will help improve the performance of this on this architecture and push it even further. So that's very high level comparison to superscalar processor, and I was going to talk, yes. Yeah. Oh, okay. So the main reason the floating point programs are significantly better is they have much better predictability in terms of control flow. They're very regular. Essentially, you have this big loop that executing over and over again. Okay. The other reason is most of these programs essentially operate on arrays, which are it's a very nicely strided axis. So you get very high level 1 cache rates as well. So those are the two main reasons why you get so much better. And because the number of functional units we provided is much higher than the 21264, you can do so much better and exploit that concurrency. That would that's part of it. The other part of it is simply that they have better memory behavior, right? More regular memory behavior. Yeah, it's also right that the control flow is less dependent on what's happening with the data. So the thing with the alpha is it's a 4-issue processor, right? But it has only 2 floating. The floating point is effectively too wide. So it's kind of, for these it's actually 2 issue, it's not 4 issue. Because of the way, the details of the microarchitecture. Yeah. It would probably be close to 3 or 4 then. Yeah. Mm-hmm. So in some sense, I'm almost tempted to say this is just simulation noise rather than anything else. So we are simulating very close to the same regions in the program, but I mean the difference in the bars I think is almost meaningless. And if you did a different region, you may actually be the parser may be worse than trips may be worse than alpha. There's another program which is we have this encryption kernel where SHA basically where you're doing the exact same thing, right? So on that the memory system becomes a bottleneck. All of your data is in one single tile. You can exactly get one request out every cycle. On that actually trips is about 8 to 9% worse than the alpha, essentially because of these routing issues. Yeah. So we are 8 times. In one sense, you could say we are 8x better, or not better. 8 times more resources. All right. So let me skip a couple of slides and get to a floor plan picture. All right. So here is actually a picture of the physical floor plan of the chip extracted from one of the CAD tools. The main point here is to show that the physical floor plan is very similar to the logical diagram that I showed you a little while ago. So these are the execution tiles, these green ones. This forms one processor we're building. This is another processor. That's a level 2 system. And this is the full chip that we're building. It actually has 2 processor cores on it. And these long rectangular skinny things you see are the instruction buffers and the data storage buffers in each and one of these execution tiles. And as I said before, by going through the exercise of actually building the chip, we've been able to do a lot of complexity analysis And one of the things we came away with was the operand network actually takes significant area. So we're now looking at some techniques to how you can bring that down by probably having smaller router buffers or using different types of circuit techniques to actually build the router. So some of those we're exploring as part of future work. But those are the main points I really wanted to make here. So there's a lot of engineering gone into this. We spent a lot of time on this. So I have to talk about some of those decisions on the one-on-one. Yes. So the alpha would actually be, so here we have put two processors and a memory system, right? So alpha was not a dual core processor. So so alpha would be approximately, I think around, I think it's around 20 to 30 million transistors, but I could be off by a factor of 2. But yeah. So where were you going with that question? Oh yeah. Oh yeah, absolutely. So you're absolutely right. So the processor itself is 4 times the area of the alpha processor if you deleted the memory system. Okay. So yeah, we're taking 4 times the area. But the point here is, I mean, there are almost no other techniques that can burn area to get performance, right? The multi-core chip, you put 2 processors that are independent of each other. So yeah. So yeah, so there's a little bit of noise in ISA, and we have done a measurement of actual clock cycle count and wall clock time. So we can talk about it offline. Yes. So that goes back to the scalability question from before. So as part of building this specific prototype, we felt that it would be better to put 2 processors and evaluate some of these multi-core effects and so on, rather than building one single chip that was really, really wide and explore that scalability aspect. So it's more of a kind of a business decision from an academic viewpoint than a completely technical decision. We also felt that you could scale our simulators to see what an 8x8 processor would be. It would be much harder to evaluate some of those system level multi-core effects in a simulator than using full hardware. So the area was another concern as well. We would have had to, actually this is the biggest package that IBM has. It probably wouldn't. In fact, So we made this design decision even before we kind of did our first floor plan. Like it didn't make design or research sense for us to build an API. In fact, this memory system is half of what we actually wanted to build, because of area constraints we had to shrink the level to cache by half compared to what we initially thought we could put on chip. You got a question in the back? Okay. All right. So let's actually move forward quite a bit. Okay, well, let me very quickly talk about this. So this is actual board that we have. So we just got this back in the lab a week ago. The main point here is the system we are building. These strip chips act actually as co-processors, and the main processor is this PowerPC chip that sits on the board and controls these as the host processor. And this is where the actual TRIPS chips would sit. So they sit on top of the data cards mounted on top of this board. And we have an FPGA whose main job is essentially debugging, and if you wanted to route different types of I/O to the TRIPS chip. So that's all the point I wanted to make here. So I'm going to skip. So I was going to talk a little bit about the prototype design and our design experience. The main point here I want to make is that by going through this very tiled approach, we've been able to bound the complexity of each of these tiles within this very small region and carry it through the entire design process, all the way from specifying the designs and thinking of the logic design to the Verilog coding, verification, physical design, all the way through. This tiled approach has helped a lot in the scalability. So that's the main point I wanted to make here. And let's see. Okay, my contribution. So since it's a big project, let me talk about this a little bit, and I skip forward quite a bit. So I've been involved very heavily in the actual definition of the ISA and building this tiled microarchitecture. So I've also wrote several simulators as part of the exercise and several lines of Verilog distributed through different parts of the chip. And I was the main verification lead for the processor and the physical design lead for the full chip. My experience spans all the way from doing spice analysis for the package and the chip I/O to kind of decide what a noise margins could be, all the way to the microarchitecture, was also involved in writing one of our first schedulers as part of the compiler. So that's where that's kind of the context of my contribution in this project. So I'm going to skip a bunch of slides and go to my summary actually. Alright, so related work. So conceptually our work is most closely related to dataflow, as several of you already observed. And dataflow has a very rich history, not over here, and there have been several other contemporary projects of it. Physically, this very closely resembles a tiled architecture. Again, there have been other implementations in academia and industry as well. There have been other approaches to concurrency also. So Multiscaler developed this notion of building these very large blocks and having control between them, sequencing per unit. And transactional memory is kind of becoming very popular now to increase performance of these programs. There have been other approaches to get concurrency as well. So those are kind of the main related work in this context. And to summarize, what we've done here is essentially these three principles that I've tried to focus in this talk. To rebalance the compiler hardware effort and eliminate centralized resources, amortize the instruction level overhead. We've done this by providing this new class of ISAs called Edge and implementing a very tiled microarchitecture with a well-defined communication network. So in terms of performance, we should demonstrated this to be 5 times better than the best superscalar process. So that's a summary, and let me very quickly talk about at a very high level some of the future work that I am interested in or other directions I would like to take. So my main view is to try and think about systems, what they would look like 10-15 years from now. The main constraints there are energy efficiency without compromising programmer productivity, at the same time getting very high performance. So I want to look at this from both the technology and the software standpoint. So in terms of technology, process variation and reliability are going to be the very big constraints. In terms of software, I think at some point we'll have concurrency constructs at the language level as well. There's several ideas being explored right here. So in terms of the architecture, I think my opinion on what this boils down to is, from a world where you're trying to find 2 or 3 parallel instructions, you're going to have to be able to manage this abundant level of amounts of concurrency that is potentially being expressed by the programmer. So the job of the hardware now becomes how exactly to find the critical components of the program and schedule them as close together as possible to exploit locality while trying to get correctness and being within your power budget. So kind of at the high level, you want this to be agile at many levels. You want to manage the fundamentally unreliable hardware and also manage this concurrency by not having to shoot through your power budget. So those are some of the high level ideas that I'm interested in exploring. I need to find out how this fits in with the context of the ongoing work over here. So here is this work has been done jointly with my advisors Steve Keckler and Doug Berger. Several other students have contributed to many parts of this tip and have played a significant role as well. With that, I can take more questions. Thank you all for listening.